off we go. Let's talk about a few things. I think we'll have time to get to every topic, but we won't be able to finish them all in full. Let's talk about logic, circuits, and binary. Oh my. Let us begin. So the first thing I want to talk about is logic, because it is the backbone of both computer science and critical thinking, which is kind of why we made this class, I guess. So in logic, we are trying to prove things. We're trying to say that, yeah, my argument is correct, or this mathematical concept is real, something like that. We're trying to prove that something is the case. And in logic, things can be either true, so yeah, provable, good, or false, incorrect, not provable, stuff like that. So those words are going to be propping up all the time. And yeah, so things can be true or false in logic, but the first question you might ask, because there's a philosophical flavor to this class, is what is the word truth even mean? If we're trying to figure that out, if we're trying to prove something true, what does it mean to be true in the first place? So let's learn some new terms and some ideas. All right, so here is some terminology first of all. I highly doubt this is going to be the right size the first time. Let's see. That's better. All right, so a statement is, and by statement I mean logical statement. Whenever I say the word statement, I'm talking about logic. So just plop the word logical at the start of that. Logical statement. A statement, another word for that is proposition, by the way. There's even another term for that same thing. A statement or proposition is a sentence, so like English, that can either be true or false. All right? It's something that you could say, yes, it's true, you can prove it if it's provable, and you can disprove it if it's not provable. But what a statement / proposition can't be is both true and false at the same time, because then it's not a statement. Then it's not a proposition. All right? So here's a sentence that is not a statement, that's not a proposition. This one, in quotes. This sentence is false, because if I told you that, right, what are your options? It's supposed to either the sentence is true or false, right? Either this, in quotes, is either true or false if it's claimed to be a statement. So this sentence is false. What happens, right? What happens in each case? If this sentence were true, that means we should trust it. This sentence is false. So if it were true, it's supposed to be false. That makes no sense. Okay, so maybe that was wrong. Maybe it was incorrect to think that it's true. Maybe it was a false statement. So if this, between quotes, is a false statement, that means it's lying to us. So this sentence is false. If that's false, then it must have been a true statement because it told the truth after all, didn't it? So if it was false, it was supposed to be true. So in either case, it contradicts itself. There's no assignment of true or false that would actually work. In either case, it's supposed to be the opposite, and that's called a contradiction. So it can't either be, it's neither true nor false. It's nothing. It's not a statement. Contradiction. That looks like an A, sorry. Contradiction. And so that's a theoretical term, too. That's a technical, logical term, contradiction. It's contradicting itself right there. It can't be either. But most sentences that we use, most English statements that we say in our day-to-day life is a statement. It can be shown to be true or false, right? But some things look like this. So in a perfect world, if everything were glorious, then we would always be able to prove that every true thing is true, and always be able to disprove or prove false every false thing. But sadly, we live in a non-perfect world, and that's not really going to work out. But that would be our goal. In that case, should the word truth then mean all the things that we can prove? Is that a good idea? So that could be our worldview. That could be the way that we look at truth. But there's a bunch of different ways that philosophers argue is the right way to think of the word truth, to be what it means to be true. All right, so I'm going to teach you a few theories. They're all very weird and head-scratchy. I'm not a philosopher. I'm a computer scientist. I don't think any of you are trained in philosophy very strongly, but if you've taken a philosophy class and I say something wrong, please shout out. But let's go through this together. These are different competing theories of truth, of what it means for something to be true. Something as simple as that idea that we maybe haven't thought of before. All right, so here's the first one. This one kind of makes sense. So we say that a statement S in the correspondence theory of truth. So there are correspondence theorists who believe this. They believe that a statement, call it S, is true if and only if that S corresponds to a fact. All right. So if and only if will plop up a lot in logic. It's a special kind of logical term. You'll hear that. I'll talk about what it really means later, but just it's part of a definition. If and only if S corresponds to a fact. All right. So that's kind of saying that, all right, you look at something, you confirm that it's there, and it all works out. So like you get out a magnifying glass. Like Sherlock Holmes would probably be a correspondence theorist, because he'd go out with his magnifying glass, observe like, oh yeah, grass is green. That's true. Something like that. Okay? So that's what correspondence theorists believe. They believe that true things are facts, things that correspond to facts. And then you could go even further down that rabbit hole and try to define what the word fact means. But then you have to get into like metaphysics and stuff that I'm not very familiar with. So let's not go there, but you could take a philosophy class if you're interested in this stuff. So yeah, their idea in the correspondence theory is that true things that you could prove and show, correspond with reality. So to a correspondence theorist, like they could go and snow is white is a true statement to them, because like we can go up to the mountains, to the Sierras, and like observe snow being white in the winter. Like we don't have to take somebody's word for it. We can go and look at it ourselves with our magnifying glass. Okay? That's the idea. So true things correspond with reality, and that is what they take to mean the word fact. All right? So that's correspondence theory. This should be a little fuzzy in your brain. Right? This is odd for somebody to try and attack what it means to be true. I don't think any teacher's done that for you before, most likely. So here's a silly meme with correspondence theory as its basis. Read that as I prepare for the next slide. Because there's plenty more. There's plenty more where that came from. All right. The next one is called coherence theory. So what do these people think? Coherence theorists. There's actually a bunch of competing coherence theories, but I'm going to tell you just one of them. They think that something's true, a statement S is true, proposition P is true, because it matches other true things, right? There's some matching idea going on there. So they think that, all right, 2 plus 2 equals 4. That statement's true to them because they can go and pick it apart. They know what 2 means. They know what that symbol means. They know what the symbol 4 means. They know what the symbol plus and equals mean. And based on their knowledge of those smaller pieces, this bigger statement makes sense to them. It follows from that. All right. So again, it's a little vague. It's a little weird. Very technical and philosophical. But that's what it means for something to be true. They can break it down into those pieces. It matches those other true things that make sense in their brain. Okay. And their ideas. So yeah, there are multiple coherence theories. That's one of them. Here's another kind. A statement S to some different kinds of a different branch of coherence theorists. They think that a statement is true when it matches the beliefs of a majority of people in society. And I think we've taken enough history classes to know that that's a horrible idea for what it means to be true. All right? For something to believe in. All right, so that's coherence theory. It's another way of looking at truth. Thinking about what it means to be a true statement. All right. Couple more, then we'll move on and have our brains recover. So the next one is called deflationary theory or redundancy theory of truth. And to these people, they just laugh at us trying to even have this section of slides because they think that it was silly to say truth in the first place. They're kind of sidestepping this problem because like saying that this statement, 2 plus 2 equals 4, is true is redundant. Why did you even use the word true? Just say 2 plus 2 equals 4 and worry about like the definition of equals or something. There's no need for the word truth. There's no need to define it to them. And so why should we care about what truth is? This is a wasted effort. Which I guess makes sense. And this is a theory. This is a theory of truth where they don't like the word truth. And again, I'm not too much of a philosopher to fully understand this, but hopefully that makes at least a little bit of sense to you. They don't think it's necessary. They think it's redundant to even think about defining truth because it is what it is. Use a different word. All right. Last theory of truth. This one is very utilitarian, I would say. It's the pragmatic theory of truth. So let's talk about this one. To pragmatic theorists, something is true to them. It's a true statement. It's a true idea. If it's useful to believe. A proposition is true if it is useful to believe. Which is kind of interesting. It's about the utility of that idea. Like, if I want to believe this, if it's going to help me, if it's going to lead to a good payoff, all right? So here's another definition from Encyclopedia of Pragmatic Theory. So they say that another way to define it is beliefs that lead to the best payoff, that are the best justification of our actions, that promote success. Those are the things that are true, according to the pragmatic theorists or the pragmatists. All right. So it's all about utility. John Stuart Mill would love this. And so here's like, if pretend this was the middle of the pandemic or something, this could be a possible pragmatic truth to you back then. Like, I will totally get COVID if I go to the party this weekend, so I should probably stay home, right? Back when the pandemic was blowing up. It would be nice to believe this as a true statement because it would probably get you to not go to that party and like get sick and like infect your family members or something. But maybe it's not true to other theories. Yes.
So even if it is a lie, it can be considered true.
Yes, exactly. So that's what it means to be true. Some people believe things that we think to be lies, right? That's how the world works. So that's truth in a nutshell. It's weird. Good question. Any other questions? All right. So yeah, we're all human. We have some definition of truth in our minds, and I wonder which one you guys are thinking of. Maybe we're correspondence theorists. Who knows? Think about which one you are, maybe. But that is the last theory of truth that I want to talk about today, right? So you can, some things are true to these theorists that maybe aren't exactly true to you under whatever theory you're using, and that's important, right? So this is probably very confusing, and that's why we have these in the slides. What I'm trying to get at is that there is no right answer, even to the idea of truth, surprisingly. So that's kind of disgusting, and maybe we all need to become philosophy majors to like reconcile this in our minds. That'll be the job of another class. So yeah, if we're happy and our brains are mushy enough, let's move on. Any last questions before I switch gears? Because we want to be able to prove things. That's our goal. And to get there, we need to understand what truth is, and now we know. So let's talk about Boolean algebra, invented by our dude George Boole from the first day of class. Back in the 1800s, he invented this. And then also truth tables, which will help us learn some new symbols. I'll define them in terms of these things called truth tables. All right? And the goal is we would like to be able to say something and have everybody understand it. Because like when we speak English, read the meme, for example, when we speak English, there's tons of contradictions in our words. Like we write something and somebody else who reads it will interpret it in a way that potentially is completely different from what we meant, right? I'm sure you've had that happen. So English is full of both contradictions, like our first example that wasn't a statement, and ambiguities, which I'm sure you've heard of and had applied to your statements. And so that begs the question, is there a better way? Is there a way to write something and have everybody across the world agree on what it means? And yes, there is a way if we write it in logic. All right, so we want to be able to formally specify our statements using logic. All right, so get rid of these ambiguities, formally specify things so that everybody understands. All right, and so let me try and motivate this topic. And let's go to the written ice page. Did everybody do attendance? Can I stop that? You didn't? So yeah. Oh, okay, yeah. If anybody forgot, I'll stop it after this question, let's say. So go to the written ice page, I'll clear it out. Boop. And here's what I want you to get into groups and think about as a peer instruction unit. So here is helping me motivate this topic. So let's say you go to a restaurant and you order coffee, and the waiter asks cream or sugar. They say that to you. And then, switch gears, you're at home after dinner, and mom says you can have a cookie or ice cream for dessert. And so both of these statements have or in them. Please take a minute to discuss with your group the difference between those two ors, because they're different ors, aren't they? Same or, different meanings. So see if you can write down as many differences as you can find on that written ice page in a couple minutes. Okay? So there's a difference between those statements. Can you find it? English is fun.
But for the mom, or I have one or the other. So I think that's what you want me to write that down. All right. So in my group, no, no Hitler's in this one.
All right, take another minute or so to get those responses up in there. Press submit. And then we'll talk about them. All right, I hope that was enough time. Finish those thoughts. Press submit, and let's take a look. Cream or sugar, you can have a cookie or ice cream for dessert. All right, let's see here. Waiter's offering cream or sugar, but with mom, it's either a cookie or ice cream, not both. Okay, yeah, that's the key. All right, the waiter's orders for like which type. The mom's is for this or that. Yeah, I think what we're trying to get at is one is giving us a choice of like we could have both if we want it. One is not. Mom is making a statement, right? She's saying, no, you can have one or the other. I'm not letting you have both. Okay? Did we see that? So, good job. All right. I'll stop attendance while I'm thinking about it. So that's exactly the idea, right? So cream or sugar, we're using the word or in both sentences, but they mean something completely different. The waiter is saying, I can bring you cream and sugar if you want both, right? They're implying that. You can have both. But mom is saying you can't have both. Have a cookie or ice cream. I'm not letting you have both. Pick which one. So that's the same word, means something completely different. We don't like that. So let's translate this to logic, to symbols and things where there is no ambiguity, like there is here. That's our goal. All right, so that's my motivation for this topic. So let me teach you your first logical symbol. It's called inclusive or. And there's, of course, two different kinds of or in logic because there's two different kinds of or that we use in English. So this one's called inclusive or. Its symbol looks like this, a V. It's like you can have one or the other. Like one on this side versus this one together. All right, so here is the truth table. This is called a truth table right here. This is the truth table for the inclusive or logical combinator. It looks like this. And here's what it's saying. It's saying, all right, here are all the possibilities for two things, because you could say this or that, this or that, this or that. And it could be either true or false, those things. Do I want it yes or no, true or false? And here is the combined, the or on those two things. All right, so this is, think of A like cream, B like sugar, and A or B as like cream ORed with sugar. This will make sense once I explain it. ORed with sugar. And so the symbol would be A, this thing, B. That stands for OR. All right? And so this, the result is true when you could say something like, I had cream or sugar. This is how you would use this logical combinator. Cream or sugar. It's the waiter's definition of OR. Inclusive. So here's the idea. If this sentence is true, right? If you had both, right? If I told you I had cream or sugar today in my coffee, then if I had cream and sugar, if they're both true, then that's still a true statement, right? I had cream or sugar, A or B. That is truth. Yes, that is a yes answer. I had cream or sugar. If I had both, it's true. All right? It's a true statement. If I had cream and I didn't have sugar, so it could be false, that's another possibility, then it's still a true statement to say I had cream or sugar. Does that make sense? So I had one of them. That's the idea. That's how I want you to interpret this. If I didn't have cream but I did put sugar in my coffee, then it's still a true statement to say or. I had cream or sugar because I had one of them. So it's one, the other, or both for inclusive. Right? The only time this is a false statement, it's a lie, if I say this and I didn't have cream or sugar in my coffee. They're both false. Then this was a lie for me to be telling you that, and it was a false statement, right? I had cream or sugar. No, I had neither. How dare I say that to you, right? Does that make sense? That's how you read these tables. In this. Good. So this is what or means. This is the first kind of or. This is the waiter's or. You could have both if you wanted to. True ORed with true, inclusive OR style is true. All right? That's the first one. I had cream or sugar. The other kind, mom's OR, is called exclusive OR. All right? XOR for short. The symbol for that is a plus sign with a circle around it. And I don't know why they use the X instead of the E, but they do. So this is the idea for this one. So you have, oh, sorry, I forgot to talk about this thing up top. I think I kind of said it. So if you want to prove that A or B is true, first of all, like I want to prove that A or B is true, so that means I could be in any one of these rows, then you have to show that A or B or both are true. So like either A is true or B is true or both are true, because in any of those cases we're going to the true side of this. That's how you can prove that statement. All right? Show you're in one of these true things. That's how that works. All right. This is exclusive OR. This is, again, the truth table for it. And think of A as cookie and B as ice cream, as A and A XOR B as like you get to have a cookie or ice cream. All right. So this is mom's exclusive OR because you can have one and not the other, and that would be a true statement. Like mom is telling me that I can have cookie or ice cream. That's a true statement. I could have the ice cream and not the cookie, and it would be true that I did that, right? Mom would be saying the right thing. I still can't have both and have said like I had a cookie or ice cream, right? That's still false. The one time it's different is here, in this place. Let me go back and forward quickly. You see the difference? Boop. That's the one row where it's different. You can't have both. This is what it's saying. A and B cannot both be true for it to be exclusively ORed, all right? Only one or the other, not both, can be true to prove this, all right? Cookie exclusive ORed with ice cream means you could not have had both. Does that make sense? That's the idea. So if you want to prove that A exclusive OR B is true, you have to prove that you're in, again, one of these rows, the true rows. So you have to prove that you have either A or B, but not both. Yeah, the other one's got to be false, right? And so, like I was saying on the previous slide, I want you to think about the idea of falsehood, of not being able to prove something. Think of it in terms of someone lying to you. Think about false as if someone was lying. Let me write that cleaner. Okay, so this is mom saying you have cookie or ice cream, It's a true statement if I had a cookie and not ice cream. It's a true statement if I had ice cream and not a cookie. It's a false statement if I wasn't allowed to have either. Mom was lying to me about having an option. And it's also a false statement if I had both, because Mom was implying that I could not have both. All right? Does that make sense? That's exclusive or. Those are the hard ones to get right. Usually we use inclusive or mostly in computer science, but exclusive or is useful too. Next comes and. It's exactly corresponding to what and is in English, which is nice for once. So this is the symbol for and. It's called the dual of or, and this is why the symbol is upside down or. It's like this wedge shape. And makes a lot of sense. All right. So let's think about it in terms of this statement. Saying like we have cream and sugar. This is the waiter telling us this. We have cream and sugar for you to choose from. So this is the word and in the sentence, and it corresponds logically as you would expect, which is nice for once. So think of A as cream, think of B as sugar, and this is A anded with B. And so here's the only time it can be true, right? The only time that this statement is true is if, yes, they really do have in the back cream and sugar at the same time. And means they both have to be true for the final thing to be true, right? That's my statement. It's only true. The only time it wasn't a lie is if we really did have cream and sugar in the back. If we had cream, but we just ran out of sugar, then I just lied to you, right? It's a false statement. False. If we don't have cream, but we do have sugar, I still lied to you when I told you this. We have cream and sugar, right? It implies that you have both. And of course, if you don't have either, obviously the and of them is false. It's a lie to say that you had both when you had none of them. Okay? So the rest is false. The only time an and is true is if they're both true. So to prove A and B is true, then you have to prove A first and then also show that B is true. Right? Prove that A is true and also that B is true. That's the only time you're in this row of the truth table. The only way to make it true. Does that make sense? That's finally like English. This one is not ambiguous. And is and. So to prove A and B is true, you got to show that A is true and also that B is true. It's the only time that works. Every other time is false. All right? And so, yeah. That's and. It's the dual of or, because like there's only one way to make and true, and there's only one way to make or false. There's some very powerful mathematics going on there that you'd have to wait till grad school to understand. But it's cool. But that's the and combinator. There's one more that I want to show you that I want you to actually understand, but I'll show you some others later. This one's called not. This one's very simple. It takes one thing. All right. Not also. This is also called the negation operator. Negation operator, and its symbol is this looking thing, like an L mirrored and turned sideways. And what it does is it flips the true to false and false to true. So maybe you can remember the symbol is like this is a diving board and somebody's like about to jump off and do a flip. Whee. Something like that. How do you draw a flip? I don't know, like that. There. And this is what negation does. So like here's an example statement. We don't have any cream today. But we do have sugar maybe. I don't know. So there's your statement. This is a true statement when, imagine that this is cream, the truth value of cream. This is the negation of cream, which is what the sentence is saying. They're asserting that we do not have cream. They're asserting that cream is false, right? So the only time this statement is true is when cream is false. You see that? It's the opposite. It's the opposite of what you would expect. So it flips it. Negation flips false to true. So the only time for it to be true is if the original thing was false, and it flips true to false, right? So to prove that not A is true, you have to show that A is false. That's the one time you're in the true section of that truth table, right? Any questions about that? It's a little weird because it's like the opposite. That's what negation means. It's giving you the opposite of something. It's true when the original thing is false. It's weird to think about. And so we now have a very powerful tool belt of operators. Here's a fun fact. With a clock signal that you'd have to like take an engineering class to understand how to make like some weird electronics involved in that. With that pulsing clock signal and inclusive or, and not, you can make a computer. These giant ones, in fact. There's nothing you could not do with enough of these operations. You could specify what it means to be a computer and how it computes. Also, something along those lines is that means no matter what you wanted, you could make now. So no matter what truth table you wanted, if you had a million variables, like A, all of its options, B, all of its options, there's a lot of them. C is another variable you had, and it had a million options. D was another variable you had. Whatever you needed to work with, put them all there. And then here's like your final thing that you wanted. Like I wanted it to be true in this case, false in this case, false in this case, true in this case, false, this, false, false, true, whatever. Think of whatever output you want. You can make that output with just a bunch of variables combined with and, inclusive, or, and not. Whatever truth table you want to make, you can make it with and, or, and not. It's really cool. And so that leads to the idea of being able to build a computer with those as well. So that's really exciting. Just any computation essentially can be specified with or and not, believe it or not. Well, let me prove that to you. So we learned exclusive or as well. That means exclusive or is redundant. I could have specified exclusive or in terms of some combination of and or not. Let me prove that to you. So here is the answer. Exclusive or, this symbol, it's equivalent to just doing some combination of and or not. It's equivalent to doing not A ANDed with B, ORed with A ANDed with not B. That's all it means to be exclusive or. You didn't need the symbol. So you can build everything with and or not. So here's the answer. What I'd like you to do is help each other. Take out a piece of paper. I'll give you a few minutes to try this. This is good practice for a test. I want you to fill in this table that I'm about to draw that like goes from here and shows that it's equivalent, that the truth table is exactly the same. So here's the table. Here's A, all the options for A and B. Those are the variables here. That's how you build a truth table. Usually, you start from the rightmost variable, and this one goes true, false, but it could be any order as long as you try them all. And then this one goes true, false half as often. So this one stays true twice, and then goes false twice. And this is an easy way to get the standard ordering of these. If you know binary, it's counting down in binary. So here we go. I would like to prove that this is equivalent to this, and that would just mean like show the truth table for this. What does the row look like? Show the truth table for this. What does it look like? And just show that they're all the same. All right. So let's build up that answer. All right. So to build this, I need to first make like not A, so I can AND it with B. So let's figure out what not A is in each case. We're going to need a row for that. Let's figure out what not B is, because we're going to need to do the same thing, AND it with A later. Then we need, then once we have not A, we can AND it with B, because we already have that. And we could build the not A and B part. Give that a row. Then we could also do the same, because we have not B, we can AND it with A. It's like, I got this already, I can AND it with this. Not B, sorry, A ANDed with not B. And then, once we have both of those, we could OR them together, right? We could OR together this row and this row to make the biggest row. What are you looking at? This one? This is not A. The negation of A. Yeah, because I need to build up this thing. I need to build up not A and B eventually. And so I need not A first. I don't know what that is yet. I'll show you how to fill in these first few rows in a second. But all right, once I have both of these, I can OR them together. Not A ANDed with B, ORed with A ANDed with not B. And then that's this thing, that's this side. And then we know what A exclusive ORed with B is. Let's compare and see that they are equivalent. So that's going to be our goal at the very end. Okay? I'll make this one a rainbow. Whee, there. So here's how you fill this in. These are all the little pieces you need. Like the things on the right come from the things on the left. But how do you make not A from A? It's like, all right, every time you see false, negate it to make it true. Every time you see true, negate it to make it false. So, all right, this is what goes here. Well, A is true in this row, so not A is false. Again, A is true, so not A is false. A is false, so not A is true. A is false, so not A is true. Same with not B. True becomes false. False, true, and then I want you to try the rest. Let me give you these tables. I'll make them very small. But I think I already did negation for you, so you don't need that anymore. But here is and or. Here's this one. I'll put it somewhere in a second. Here is inclusive or. That's what the or means. And exclusive or we'll draw in later, if you don't remember. I don't think I can give you all of these at once. Whee. All right, my computer's going very slow right now. Got too many things open. So there's this truth table. There's this truth table. Use that to fill in all these. So you got to and these together. You already have them. And these things together. You already have them. Then you have both of these. You could or together. And then see if you remember exclusive or. See if they're the same. See if the column becomes the same thing, because that's what it means to be equivalent. All right? So give that a try. And then I'll fill it in after you. So it'll take a couple minutes. We have to push around the symbols for a while before we're comfortable with them. That's why we're doing this. Let's see if you remember what exclusive or looks like with every combination. Does it make sense? I'll show you the answer in a couple minutes, in a couple seconds. So this is one way to show that one thing is equivalent to another thing, to show that their truth table columns are equivalent. So they have the exact same values. So, all right, I'm trying to work up to this. This is why I have all those intermediate steps. I want this. Now I can build not A ANDed with B, because I have a not A column and I have a B column. Let's use them. Those are all the options. So, all right, not A is false here. I need to fill in this one. False ANDed with true is false ANDed with true. No, sorry, that's or. False ANDed with true is false. Anything ANDed with false is false. So that puts false here. A little bit faster. True. Oh, sorry, wrong column. False ANDed with false. That's not A. This is the B column. I'm ANDing those together. False ANDed with false is definitely false. Reading off the table. True ANDed with true. Ooh, this one's true. Cool. There's a true there. And then, all right, what about this last one? True ANDed with false. Oh, no. All right, so one of them was false, so that makes the whole thing false, right? You have to both be true for the final thing to be true. So that's how you fill in that one. Then we have A ANDed with not B. So here's our A, here's not B. For this one, true ANDed with false, false. They both got to be true for it to be true. A ANDed with not B. Oh, this one's true. Cool. True. False ANDed with anything, right, is false. So both of these last ones are false because the A side is false. Cool. And then I got to OR them together. So OR this one with this one. So it's this column with this column. OR them together. It becomes true if any of them are true. Inclusive OR. So false OR with false is false. False OR with true. Ooh, one of them was true. So true. They can both be true for inclusive OR as well. True OR with false. True. False OR with false. False. And what do you know? Remember A exclusive OR B? It was false, true, true, false. It's all the same. This is false, this is true, true, false, assuming A and B are these things in that order. What do you know? In each case, they're equal. So that means this big thing is the same as this thing. It's saying the same thing. It's equivalent. All right, so that was our proof. We just proved that one is the other. Any questions about that? We're trying every possibility. A and B are the variables. These are all the different possibilities of true and false for A and B. Okay. So here, these are the values of A and B that I'm considering for as I'm working on this row. Okay? And if we try them all, we know every possible outcome. If there were 3 variables, you'd have to have 8 rows, because there's 8 options at that point once you bring in the third thing. We'll get to that. Any other questions? It's good to know how to do. I'll give you some more examples, though. So that's fun. So you can build a computer out of and or not, but this is capitalism. We can't have that. Let's do better. So let's talk about NAND and NOR. So and or and not, these symbols, and or and not, taken together, they can build anything, any possible truth table. And the word for that is functionally complete. So all these things, you can just use and or not in some combination. Those are functionally complete. You can build any truth table. Whatever you want out of and or not. There are some cooler ones that are themselves functionally complete. So here's an operation called NAND. NAND by itself, just some combination of a bunch of NANDs, is functionally complete. That's super cool. So here's what NAND is. It's just, it's first do A and B and then take the negation. So starting with A and B, and them, and then negate that. Negate this row to make this one. That's what NAND is. That's its output. Apparently, just a bunch of NANDs can build any truth table. It's really cool. And so if you're building a computer, just build one thing that can do NAND, and then you just have to mass produce that. You don't have to build 3 separate things. That's the reason we care about this. There's another one called NOR. It's the negation of A or B, called the NOR operation. It's also functionally complete by itself. So that's really cool. So you can build a bunch of NOR things and make a computer out of that if you would prefer. I think everybody is happy with NAND these days, though. Up to you. So yeah, that's pretty cool. Functional completeness is a powerful concept. It means you can build whatever you want, including a computer. Right? Okay, so let's get some practice with building these formulas and then building truth tables as well. So here's a statement. All right, here's like Dad says, "I'll give you $20 if you clean the bathroom and, in parentheses, mow the lawn or do the dishes." Okay, so you see how I'm reading that. So we want to, as somebody who wants money, what we have to think about, what conditions are we guaranteed to get $20? So we can pick the easiest one maybe. Okay. So let's think of clean the bathroom as A. Let's think of mow the lawn as B. And do the dishes as C. And so what is the statement saying? I'll give you $20 if A is true, so I clean the bathroom, and this is all in one parenthesis statement. A and B or C is true. Mow the lawn or do the dishes. See how I'm translating that? So now we have the symbols. We can see which options end with true. Okay? Under which conditions are we guaranteed to get $20? Right, so let's make a truth table for this formula here. A and with B or C. See which ways we can make true at the end. Which ways could it be true? All right. Here we go. So A, this is B, this is C, and we're trying to figure out A and B or C. What are all the ways in the truth table that this could be true? And so we have three variables. A gets to vary, B gets to vary, C gets to vary. And there's a bunch of different options. You think they all have two choices, right? This could be true or false, this could be true or false, this could be true or false. And it multiplies, so it's 2 cubed different possibilities, so 8 total. And if we follow the pattern, here's like the standard way of writing the order of possibilities. But as long as you get all 8, it's fine. This one just keeps on rotating. True, false, true, false, true, false, true, false. This one stays true a little bit longer and false a little bit longer, so true, true, false, false. True, true, false, false. This is a good way. This is an easy way to get all the possibilities quickly. And then this one stays true and false even longer, twice as long. True, 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 true. False, 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 false. And we needed 8 of them. So these are all the different combinations of A, B, and C. Every single one is accounted for. So this is all the different ways that this could go. And now we need to build A and with B or C. So we need to do B or C first before we're ready to AND it with A. So let's calculate that. B ORed with C. So luckily those are right next to each other. What's true ORed with true? That's true for here. True ORed with false. True. False or true. True. False or false. Okay, that one's false. True ORed with true. This is inclusive OR, by the way. They're both allowed to be true, so true. One of them's true. One or both are true. One or both are true, so true. The only time it's false is if they're both false. So that's false there. So now I have B or C, and now I can AND it with A. Cool. Now I can do A ANDed with B or C, because I have all of those columns ready. So I have this one and this one. I can AND them together and get my final answer of true or false under all these possibilities. Let's see which possibilities give us $20. So, all right, we have true ANDed with true. That one's going to give us true. Cool. True ANDed with true. Also true. True ANDed with true. Awesome. These are different ways to get $20. This one, true ANDed with false. Oh no, that one's false. Darn. And then false ANDed with anything. And all these rest for A are false. False ANDed with anything is automatically false. So we have 4 falses at the end here. So it looks like the only way that we're going to get $20 is if we're in this case, and this case, and I hope you see how this is now helpful to you as a human, and eventually a computer scientist. So, all right, we can get $20 if we are the greatest child, and we just do everything. We clean the bathroom, it's true, mow the lawn is true, and we also do the dishes. If we're just extra like that, that's totally fine. We get $20. We do have options, though. This one's an or, not an and. So, all right, we're forced to clean the bathroom, first of all. You see that? We are forced to clean the bathroom. The only time this is true is if that's true. That's an and part. That had to be true. And then, all right, we could get $20 if we clean the bathroom and we mow the lawn, but we don't do the dishes, because we're allowed to choose one of those. That's what the or was saying, and that's explicitly made true here in the end. All right. Alternatively, we could clean the bathroom and not mow the lawn, but then we do have to do the dishes, right? That was our other option. That's our third way of making $20, right? It's kind of logical, right? Do you see how this is all being translated from English, which is ambiguous, to logic, and then we're extracting information from that truth table? Any questions about any of that? So that's useful. Useful for our everyday lives, yeah.
Actually, so on line 6, you said that would be or C. You said that is true.
Oh, did I mess up somewhere? 1, 2, 3, 4, 5, 6. This one? B or C is true because the B was true. And or is true if either of them or both are true.
Okay, so as long as the first one is true, that means it's true.
Yeah, the whole thing's just like, is one thing or the other true? That's what or means. And so going back to the truth table, that's inclusive or, by the way. So or is true most of the time. The only way to make or false is if they're both false. If they're both true, it's true. If one and not the other is true, or if the first one's false and the second one's true, still true. The only way that it's false is if they're both false. Yeah. Good question. Any other questions? So hopefully we'll get $20 now. now that we know what to do. With that in mind, I have a question for you, all right? Let's say that we have an even more complicated idea, something involving 3 variables again. But here is your new formula. A AND with B, then take all that OR it with B AND with not C, all right? This is your new formula. Try and create a truth table for this. I want to see what this final row looks like. Use all the intermediate rows if you need to. I'll give you a minute head start. Try doing this. And here's from before if you want to remember the order. This may or may not help. You have to look up the truth tables online. I can't fit them all. But take a minute, give that a start. Come up with all the possibilities for A, B, and C, and start building up this truth table. So maybe you want to do A and B separately, then you want to do not C, then you can AND B with the not C that you just made, and then once you have both sides, you can OR them together. You see how like the last thing to do is the OR? You gotta have both first. So I'll give you a minute head start because we need to do a few more things. Can't give you too much time, but I promise to show you the answer. Yes, so here's your new formula. Create a truth table to show the truth values for every possibility for this one. Yeah. Oh, if you'd like to. I don't think I'm going to look at it because I'm going to start drawing in a minute while you're still probably working. Try and follow my pattern. And if you're confused, I'll show you in a minute. Because again, maybe this is another request from Dad and we want to know which ways are we getting paid? What are our options if we're lazy? All right, let's see how much of this I can copy and paste because that would be glorious. I will save as much of my wrist as I can. Oh yeah, that is gorgeous. All right, so here are all the different possibilities for A, B, and C. What do we still need to do? Well, I eventually need this whole thing, but here's a piece and here's a piece that eventually need to be ORed together. So let's do A and B first. So I can have that chunk just ready to go. What's A AND with B in all these cases? So true and true is true. True and true again, true, false, because the right side's false because B is false here. And then A is false for the rest of these, so they're just all false. False, 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 false. I'm doing A AND with B. And then for this one, I do B AND with not C. I don't have not C yet. I could calculate it in my head if I wanted to, but I just want to show you how to do it all out together so you can just read it off, doing one thing at a time. So what's not C in all these cases? The way that I wrote it goes true, false, true, false. So every time you negate something, true becomes false, false becomes true. So now it's just going to be false, true a bunch of times. False, true, false, true. False, true, false, true. So there those go. And now I have the not C row, or column. And now I have the B column. And now I can bring them together with an AND, because they're meant to be ANDed together. So B ANDed with not C. Alright, I got my B, it's true in this case. Not C, ANDed together with false. Darn, one of them was false. So the whole thing's false. B ANDed with not C. True and true, cool. There's a true. False. And with false, okay, false just immediately makes false, so that's useless. This side's false, I don't even need to look at the other side. The result is false. Then these are true, so true and with false, darn, that one's false. And then true and with true, ooh, alright, cool, that one's true. And then false and with anything, the rest of these for B are false, so I don't need to look at the right side. False, false. That's how I get B ANDed with not C. And then finally, I have both sides. I have the A and B. I have the B and not C, and I just need to OR them together to get my final answer, my final truth table column. So take my A and B, OR it with B and not C. I've got them both ready to go. Let's take them and OR them. So this one ORed with this one. If any of them are true, it's true. So true ORed with false, true. True ORed with true is true. False, darn. False ORed with false. That's the only time it's false. Shoot. False ORed with false. Darn. False still. False ORed with false. False ORed with true. Okay. These two make true. One of them's true. Then we have false ORed with false, and one last false ORed with false. So it's false. So apparently the only way to make this true is if... Oh, we don't get to see. Well, let me fix that. I think sometimes the solution was unplugging this computer's little HDMI cord. Let's do that. Let's give that a try. Sorry about this. Okay. And then, yeah, something must have jiggled that computer or something. But at least we know how to fix it. Give me a minute, sorry. All right. Just for added suspense, I guess. What are all the ways to make this true? Well, this way is true, this way is true, this way is true. So we got false, true, and false for A, B, and C, true, true, and false, or if they're all true, it still works out. Okay? So those are the three ways, three combinations of A, B, and C to make true in the output. Okay? And so hopefully this meant something. Like this is something Dad told us, and we want to see all of our options to pick the best one for us. All right, so that is a full-blown example of truth tables. Please try this. This is very good to get practice with. I believe in you. Now that you know the symbols, should be getting a little bit better. Like you're memorizing the and, you're memorizing the or. One of the few things you have to get kind of fast at in this class. But that's truth tables. All right. So, all right, where am I going with this? I'm trying to build a computer, right? You'll have to wait till CSCI 45 to really understand, but these operations we can put inside of a computer. And the way that works is we call them not just logical operators anymore, we call them logic gates. Like we can, they're Legos, we can mix them up and put them together, and we can build circuits out of them, right? That like take some input wires and send some data along an output wire. So that's what I'm about to draw for you, all right? So that's trying to answer this question. Like, yeah, sure, this is nice. We're learning logic, yay. But how does it apply to computers and computer science, right? You can build computers out of these logical operations. All right, so here are the symbols for logic gates. All right, so this is the AND gate. It looks like a capital D, or it looks like the bullet in Super Mario Brothers. And it takes two things and it ANDs them together. It's like it shoves them together. The output is A ANDed with B. So here's the input wires. They go this way through the AND gate, and the output is A ANDed with B. All right, this is kind of cool. This is the OR gate. It's a little slightly curvier than the AND gate. That's how you remember. And it takes two inputs as usual, and it outputs their OR. A ORed with B. All right. What is it inputting and outputting, you might ask? It's electricity, electrical signals. So like an input of a true means like you're inputting the number 1, or really to an engineer this means like you're sending high voltage through the wire, a higher voltage than usual, high voltage. You have like a base voltage that means false. False is 0 is a lower voltage. That's how it knows which one to do. And so that's true and false to a computer, high and low voltages. So here's the negation, here's the NOT gate. It's, think of the negation happening in this little dot. That will help understand some of these other ones. So here's the NOT gate. It takes one input, of course, and it outputs its negation. So if it was true, it makes it false. If it was false, it makes it true. Another word for this is called an inverter in gate land. And then here's NAND and NOR, which is exactly what you would expect. Do the AND and then negate it. Like the dot means negation. Here's the OR, then negate it. Dot means negation, right? And then here's exclusive OR. It's you can have an exclusive OR gate if you want, and it looks like OR with an extra little line, extra little slash. So those are your logic gates. Let's use them to build a mini computer that computes this logical formula. So here are my gates over here. Oh, PowerPoint is not happy when I add an image. It's so confused. There. That should have never existed, but okay. There. Too many things. They need to give us better computers here. All right. So here are my gates, and let's build the logical circuit for this idea. All right. So you have to do not A and with B, and then OR that with C and with not D. All right. Also, something else happened here. This bothers me. Give me a second. Okay. I think I'll have to mess with this. There we go. Not and or and not. Something like that. Don't know what happened to PowerPoint. Sorry. That looks prettier to me. So, okay. We need 4 input wires. A, B, C, and D. They can be in any order, but I'll just draw them in this order. And so that's where the input's coming from. Somebody's sending along high or low voltages to us. And then we need to compute this final answer eventually and send that out in an end wire. So, all right, we need to first compute not A so that we can add it with B. So let's put it in an inverter. Watch. So take the A, negate it with a not gate, and now coming out of this wire now is not A. I can AND it with B with an AND gate. So I'll bring in one of these. So here's an AND gate. And so those are both inputs to that AND gate. Now coming out of this wire is not A, ANDed with B. Do we see? It's just drawing pictures at this point. All right. Then for this side, we have C and not D. So let's negate D with a not gate or an inverter. So this is not D coming out of here. And let's AND that with an AND gate. Boop. So now coming out of this wire is C ANDed with not D. And now my final answer needs to be those two things ORed together. So I'll use an OR gate. Boop. Boop. And so now coming out of this final wire is not A ANDed with B, ORed with C ANDed with not D, and this was going to do some computation that we cared about. All right? That's how you use these gates to build your final answer. Any questions about that? So here are your input wires, like the electricity's flowing that way essentially, and then output is true or false depending on the inputs. That's how you build this circuit using these logic gates. Any questions about that? Okay, yeah, just is there a specific question that you can ask about it, or is it just very fuzzy in your mind? All right, then I think the answer is examples. So here's one example. Now I want you to try. Help each other. Here are the gates. You have 4 inputs again. Let me give you my answer over here as well. Let me just give you this whole thing. If you want to look at my answer for the last one, this is not the answer to this one, but similar pattern to follow here. See if you can build this circuit. B or not C, so all that, ANDed together with this whole thing, not A and D. See if you can draw that logic gate, or draw that circuit using the AND, the OR, and the NOT gates. Let me know if you have any questions. I'll give you a few minutes to try this. And by a few, I mean like 2. Something similar to that, yes. That was the answer for the last slide. And this really makes you think about the ordering. In what order do I need these things done so I can get the right output? Figure out how to get rid of that. Words at the bottom there.
Okay, so we have to draw this out. We make a circuit for the following expressions. For that, we use the not A right there. And now we have to have a D there. So for A, D, and C, or like these not really for me. It doesn't really make sense for me. It's like
A bunch of stuff is connected to others.
yeah, it's
Which
not
are
it's not
shapes and then
All right, we're kind of running out of time, so let me just do it, and then hopefully that will answer any questions. But I like that you guys are helping each other. So here, let me do it real quick. B or not C. So you take B, you got to negate C with a not gate. Got to OR them together with an OR gate. Boop. This is my fastest drawing here. This is B ORed with not C. There's no easy way to draw this if A and D are way over here. You're going to have to jump over a wire. But not A end with D. We can do that part now. Let's negate A. So now come out of this is not A. And then we have to somehow like give that to D with an AND gate. Let's bring it down here maybe. And so here's D. And we have to put A there too. And so when we're drawing schematics like this, if you ever need to you don't want these wires to touch, first of all, right? That would short a circuit or something. Here's how you do it in a schematic to show that you're hopping over the wire and not touching it. There. Magic. And then we have our not A ANDed with D. And then finally, we want to AND those two things together, those two final wires together to get our final answer. So there's your answer coming out of here. Does that answer any questions that we might have been having? So that's the idea. It was really cool. Please study it. I think it's interesting. Question? There. I'll give you 10 seconds because I gotta move on. There's only 3 minutes of class left. All right. So that brings us to one last topic, and I think I can do it in 2 minutes. It's not a lot. We'll finish it next time, but I want to talk about binary because that's the ones and zeros that live inside of a computer. How does this all apply to everything? That's your true and false. That's the idea. That's your high and low voltage. We're working in terms of one being true and 0 being false, and high and low voltage and all of that. Everything inside of our computer is just a bunch of ones and zeros being pushed around by these logic gates. And so in the last 3 minutes of class, let me start explaining binary and we'll finish it next time. All right? So as humans, we like to write our numbers in base 10. That's called decimal. Decimal. That's our number system. Decimal. And what that means is, the reason we use deca or 10, that means we have 10 digits to work with. 0, 1, 2, all the way to 9. That's 10 digits total that we use to build our numbers. 10 digits. That's what it means to be in base 10. So if you have 9 and you try to add 1, you've run out of digits in that place. You have to add a new place. All right? And so we can make big numbers out of those digits, like 123. There are different bases, though. And I will write those using a subscript so that we don't get confused. Like this number, this could be in a different base as I teach you new bases. So just to make it clear that this is the decimal number 123, I'm going to do subscript 10 to mean like this is the base that we understand. This is 10 base 10, all right? 123 in decimal, because there's different number systems now, all right? Binary is base 2. So that implies that you only have 2 digits to work with, 0 and 1. Interesting, all right? And so if you're in binary and you try to add 1 to 1, you've run out of digits for that place. You have to add a new one. So in binary, the number 2 is 1, 0. It's not 10. This is base 2 we're talking about right now. 1, 0 in binary stands for the number 2, which is kind of weird to wrap your mind around it now. But we'll get there next time. And so, yeah, this is here's some terminology. A bit is a binary digit, so a 0 or a 1, we tried to be cute and shorten it like that. So like 101101, that's a 6-bit number. And then finally, a byte is an 8-bit number. So 8 strings of bits, that is 1 byte. All right, that's 1 byte. And these bases are separate. So this number is not the same as 1011 in decimal. And we'll talk about that next time. All right. In the last 20 minutes of class, or the last 20 seconds of class, the reason we use base 10, we think, is because we have 10 fingers. So maybe if you were living in like the Simpsons world, you'd be using base 8. So that's all that I have to say. Ended just in time. I'll see you next time. Thanks, you too. Yes. Absolutely. What do you got?
The assignment. This thing is.
Yeah, let me